Good evening, everybody. Welcome to tonight's edition of the Triangle Area SQL Server User Group's main meeting. So, one quick note before I do hand it over. Tom Norman, current board member, soon to be ex-current board member. He's leaving us for the great state of Texas. And as a result, we will have a board position open. If you are interested in running for a board position for the Triangle Area SQL Server Users Group, please do reach out to me. Hit me up on Meetup, email, or however you can get a hold of me. That position will become open very soon, and we'll figure out a mechanism for getting somebody into that VP role. If you have any questions about what the role entails, also hit me up. I did talk about it a little bit in an email to the whole group, but in case you're not on that Meetup email list, just letting you know this role is available. So with that, I am now going to hand it over to Deepthi, who will talk about the SQL Engine.
Hey everyone, thank you so much for attending this session today. Good evening. First of all, I would like to thank Kevin for giving me this wonderful opportunity for presenting at Triangle Area SQL Server User Group. It's an honor, Kevin. Thank you so much. So today, this evening, I'm going to present on the topic, Start Thinking Like the SQL Engine. So basically, this session is all about SQL Server internals and architecture. Like whenever a user submit any query to the SQL Server, once we receive the results, behind the scenes, what happens until we see the results, right? At each component, what happens inside the SQL Engine. So that is all about this session today. Hopefully you like it. So let's get started. A little bit about me. I'm a database administrator with 7 years of experience in managing SQL Server and databases. I'm a Microsoft certified trainer and Microsoft certified solution expert. I did my master's in computer technology at Eastern Illinois University, and I blog for dbanuggets.com. That's my website, and you can contact me on Twitter at dbanuggets. That's my user ID, and down below, that's my email address. If you have any questions regarding this session later, please do not hesitate to contact me. So what are we going to discuss in this session today? We are going to start with the basics, the asset properties, and how each and every relational engine should satisfy the asset properties of transaction. And we are going to see a very simple example ensuring the asset property. We are also going to see the different types of components we have inside the memory architecture of SQL Server. Especially in this session, we are mainly focusing on how the plan cache and the buffer pool are managed, because they are the major components, right? The biggest components inside the memory architecture. And then we are going to see the life cycle of a query for the read as well as the write transactions, like what happens behind the scenes at each stage inside the SQL engine. And we are also going to see the different types of components we have inside the relational engine. That's relational engine components as well as the storage engine components. So internals, why should we actually care, right? Even without knowing the internals, we can just go ahead and do our daily jobs. But many DBAs and developers, they work with SQL Server on daily basis, but they might not exactly understand what happens behind the scenes when a query is submitted to SQL Server. So knowing this information will really help you in knowing how the queries are processed at each stage inside the SQL engine. It will also help you in tracking down the performance issues very quickly and fix them efficiently. It will also build your confidence while managing the SQL engine as well as the databases. It will also help you in convincing your coworkers or managers of why they have to take your ideas seriously, because once you know about the internals, you can suggest them what we have to do and what we should not do. Last but not least, we work with SQL Server every day. So the more we know about the internals, the better we can understand how SQL engine works behind the scenes. Let's start with basics, the asset properties. Every major relational engine, it can be SQL Server, Oracle, PostgreSQL, or Sybase. All these major relational engines should satisfy the asset properties of transaction. So what is this asset? A stands for atomicity. Atomic meaning a single unit of work. A single transaction can contain one operation or it can contain multiple operations in it. Each and every individual transaction should either complete successfully or none of them. Let's take an example of a store procedure. Inside that store procedure, we have an, let's say, update statement as well as an insert statement in it. Whenever you execute the store procedure, both of these operations should either complete successfully or none of them. For example, if the update succeeds and if the insert fails, then SQL Server should go ahead and roll back the entire transaction. That's atomicity. C stands for consistency. The data inside the database should always be consistent before starting the transaction and after completing the transaction. Let's take an example. I wanted to do an update statement onto a table, right? While I'm doing that updates, let's say there is a outage, like the current has gone, like the power is turned off, and I had to restart the SQL Server. When I restart the SQL Server, that particular uncommitted transaction should be completely rolled back, making the data in the consistent state. That's consistency. I stands for isolation. No matter how many concurrent transactions are running at the same time, each and every individual transaction should be independent of each other and should not be interfering with any other transaction. Let's take an example. I wanted to insert a bunch of records into a table. While I do that insert, none of the other transactions should be interfering with my transaction. That's isolation. D stands for durability. So once the transaction has been successfully completed and all the data that has been already modified should be made to the database permanently. Like if I had to restart the SQL Server later, all these committed data, which is already inside the database, should not be lost. That means there should not be any data loss. That's durability. So what components of the SQL engine will ensure this asset property? Atomicity is very easy to be ensured. It is taken care by the parse component inside the relational engine. Consistency is also very easy to be ensured. It is taken care by the parser and binder components inside the relational engine. Once the atomicity, isolation, and durability are ensured, consistency will be automatically ensured. Isolation is all about the logging mechanism. It is taken care by the log manager inside the storage engine. The durability is the most toughest of all. It is taken care by the transaction log inside the storage engine. So let's take a very simple example ensuring these asset properties of transaction. In this example, we will take a simple bank transaction. For example, let's say I have a balance of $500 in my balance, which have an ID of 1, and I would like to send $100 to my friend's account, which have an ID of 2. I can do this simple transaction multiple ways, right? I can use the online application to do it, or I can use the mobile phone application to do it. So for this example, let's take the mobile phone application. This simple transaction have two operations in it. The first operation is to deduct $100 from my balance, which will make $400. The second operation is to credit $100 to my friend's account. So let's see what will happen once I begin the transaction on my mobile phone. Behind the scenes, SQL Server will also begin the transaction. It will go ahead and do the first operation, which is to deduct $100 from my balance, which will make $400. The second operation is to credit $100 to my friend's account, right? But I suddenly see this on my screen. I don't know what has happened, but I'm suddenly logged out of my mobile phone application and I see this alert saying facility is temporarily unavailable. Now what has happened? I do not know if I lost my $100 or if my friend has received $100. So because this is money, right? So I rushed calling her and asked if she received any money, which she said she didn't. So I just called the bank customer service guys very angrily. They said there was a severe thunderstorm and some of their SQL Server went down and they already restarted them. If this particular transaction, right, if this particular transaction is ensuring the asset property, What should happen once they restart the SQL Server? Let's go ahead and see. Once they restarted the SQL Server, this is uncommitted transaction, right? It got disturbed in between because of the power outage. So once they restarted the SQL Server, this particular uncommitted transaction has been completely rolled back, making the data in the consistent state. This particular transaction is ensuring the asset property. Now how? Atomicity is ensured by rolling back the entire transaction, and consistency is ensured by reflecting the $500 in my balance, which is the initial amount before starting the transaction. Isolation is also ensured. Like, did you observe when SQL Server went ahead and did the first operation is to deduct $100 from my balance? None of the other transactions have been interfering with my transaction. So isolation is also ensured. Durability is also ensured. I did not lose my money. My $100 is back, which is clearly reflecting in my balance, which is the initial amount, the $500. So transaction log helped made this possible to roll back this entire transaction, making my data in the consistent state. That's how each and every individual transaction of all these relational engine should satisfy the asset properties of transaction. Now let's talk about the SQL Server memory architecture. SQL Server Engine is a Windows program which will use Windows APIs to allocate memory to the SQL Server. So there are different types of components we have inside the memory architecture of SQL Server. In this particular session, let's focus on the major components, which is the plan cache and the buffer pool. But let's also see what other components we have here. The first component, which is one of the biggest components, is the plan cache. It holds the store procedures, query plans, etc.
Uh-oh, I saw a low battery alert there. So, looks like her laptop might have gone under for some emergency nap. So we're going to hold on, and hopefully she'll be able to plug in that laptop and be back here shortly. Meantime, I guess I will vamp and let's talk a little bit about this fun interview question. So Mala pointed it out. Which asset property SQL Server is flexible with? Oh, let's see. So question for this diagram, is there an OS isolation layer for OS related dependencies? We'll have to see. I'll hold that question until the end and wait for her to come back. In the meantime, as far as the asset properties go and which one is flexible, yeah, that is a nice question. I'm not sure I would have come up with the answer immediately that, yeah, isolation is the one that can be flexible with things like no lock. Hey, welcome back.
Sorry, Kevin.
No worries, no worries. We were just talking.
My system suddenly went down, so I was like, oh my God. But I'm
right.
back here. I'm back.
I was just vamping until you were able to get back on here. So Solomon, you gave the answer that I gave around delayed durability. Prior to delayed durability's release, isolation was flexible. Okay, now I'm going to be quiet again and let you get back to go.
Yeah. So you are able to see my screen, right?
Yep, we can see just fine.
Awesome. So where are we? So we are at the plan cache, right? So plan cache is one of the bigger components. I do not know if I enabled my video. I think I did not, right?
You did not know.
Yeah, let me do that too.
All right, full screen on that so that you
start picture. I don't know how to enable.
Oh, you might have to reload. It might have been that the camera wasn't available when the page popped up.
Right. So it actually disabled. I cannot enable it.
Yeah.
So that's fine, right?
Yeah, we can roll with it. I'll just full screen your desktop, and that way we'll see.
Sure. Okay. So you are seeing my screen in the presentation mode.
Correct.
Right. So the first component, which is the plan cache, which is one of the bigger components, it holds the store procedures and query plans, etc. The buffer pool, which is the biggest component of all, it will hold the 8 KB data pages and index pages in it. There are also other type of cache like log cache, token and perm user store cache. Now what this token and perm user store cache does is it will store the user permissions onto the objects. There is also other type of cache known as column store cache, which will store column store indexes in it. Now, all these caches which you are seeing in the blue color are very special. They are very special because they have a backing mechanism in them. Because they have a backing mechanism, it is very easy for these caches to be expanded and shrinked when there is a memory pressure from the SQL Server. Like, what do I mean by the backing mechanism, right? The plan cache, let's take the plan cache as an example. The store procedure, which are stored inside this plan cache, the query text behind that stored procedure is stored inside the system tables. The buffer pool, let's take another example. The data file, the data pages which are stored inside this buffer pool is stored inside the database files inside the disk subsystem. So the database files are the backing storage for this buffer pool. Now let's take the other cache, right? The log cache. The log cache is stored as a transaction log inside the disk subsystem. And let's take the column store indexes inside the column store cache. These column store indexes are compressed and they are also stored inside the disk subsystem. They can be easily expanded and shrinked because they have a backing mechanism in them, right? But what about the fixed memory, which you are seeing in the green color? Fixed memory is known as fixed because it cannot be expanded and shrinked when there is a memory pressure, because it doesn't have any backing mechanism in them. But what about what kind of things will be stored inside the fixed memory? The connections to the SQL Server, like for example, the memory grant connections that we use for the hashes and sorts, those kind of connections are stored inside the fixed memory. Now, as this is fixed and it cannot be expanded and shrinked, what will happen if more and more queries are requesting for the memory grants, right? Once this fixed memory gets full, it cannot be expanded or it cannot release those connections from one query to the other query, right? Because once the memory grant has been released to a particular query, even before the execution, it doesn't get released until the query gets executed. So what will happen when this fixed memory gets full? There is an alert system inside the SQL Server. It will go ahead and when there is a memory pressure right now, right? When there is this pressure, the SQL Server will go ahead and request these other caches, which can easily expanded and shrinked when there is a memory pressure. So let's take an example of a plan cache here. It will go ahead and request the plan cache. Inside the plan cache, those execution plans will be there, right? So SQL Server will go ahead and request the plan cache to evict these plans out of the cache such that it can get some memory for these memory grant connections. So whenever you see those memory grants, your queries are requesting for more and more memory grants, and SQL Server is allocating to those queries, it's not easy, right? It is not easy to get those memory grants. It is getting those memory grants from all these plan cache. It evicts those plans, then it is going to get these memory grants. That's how the fixed memory gets managed. Now there is some other thing known as SQL Server.exe Overhead Memory. As you know, SQL Server.exe is an executable, and many things will be running this executable, right? Like for example, the thread stacks. Even this component will come under the memory architecture. Now there is some other type of memory known as in-memory OLTP. Even in-memory OLTP also comes under the fixed memory. It cannot be expanded or shrinked when there is a memory pressure. Now, what kind of things will be saved inside this fixed memory, in-memory OLTP? Memory optimized tables, right? So as it cannot be expanded and shrinked, there should be some other process which should be cleaning up all these objects inside the memory optimized OLTP, such that it can get some memory for the newer objects to be stored inside in-memory OLTP. That's just an overview of SQL Server memory architecture. Now let's go ahead and talk about how the plan cache and the buffer pool gets managed. Now, how does this memory gets managed, right, inside the SQL Server? There is something known as Lruk algorithm, which is also known as least recently used algorithm. The -k is for the complexity of the code. Now, what is this LRU? LRU meaning if something is staying inside the cache for the longer time, those kind of things will be discarded first. Let's say there is an execution plan which got created very easily with less amount of resources, and it is not being used since long time, right? Those kind of execution plans will be discarded first. But what if there are execution plans which took so much of resources to get created? Those kind of execution plan will have a little bit of more options to stay inside the cache for the longer time. But they have to be used also, right? Because if they doesn't get used, they will be evicted. Now, how does this plan cache gets managed, right? Let's talk about the plan cache first. There are two processes which will be using this, which will be cleaning up this plan cache. One is the lazy writer and the other is ghost cleanup. Now let's go ahead and talk how these two processes works. Now this is my plan cache, the right side diagram you see. There are 3 execution plans in it, the plan 1, plan 2, and plan 3. My plan cache is really small. On each and every object we see here, inside the plan cache, we have 2 numbers at the bottom of each object. The left side number is known as complexity code value, and the right side number is known as complexity countdown value. Now, when the lazy writer kicks in every minute by the SQL Server automatically, it will go ahead and check if there are any least recently used execution plans. In our example, none of them will be used right now. So the lazy writer will go ahead and decrement the complexity countdown value for the plan 1 by 1. Each time it finds it is not being used, it will go ahead and decrement the complexity countdown value by 1. So here, none of them will be used. So it will go ahead and decrement the plan 1 complexity countdown value from 18 to 17, for the plan 2 from 9 to 8, and for the plan 3 from 2 to 1. And the lazy writer will go away. In the very next minute, the lazy writer will kick back in again to see if there are any least recently used execution plans. Right now, none of them will be used again. So it will go ahead and decrement the complexity countdown value for the plan 1 from 17 to 16, for the plan 2 from 8 to 7, and for the plan 3 from 1 to 0. Now, did you observe the complexity countdown value for the plan 3 has turned to 0? That means the SQL Server should go ahead and evict this plan out of the cache, right? But that is not what it is going to happen. There is some other process which is known as ghost cleanup. Ghost cleanup will be kicked in every few minutes by the SQL Server automatically. Now, whenever it gets kicked in, it will go ahead and check if there are any objects which do not have any countdown value on it. Now, in our example, plan 3 doesn't have any countdown value, so it will go ahead and flag this as ghosted. That means this particular plan is still inside the plan cache, but it is in the half-life. For example, there is a memory pressure tomorrow, right? When there is a memory pressure, the ghost cleanup, it will get kicked in and it will clean up all these ghosted execution plans out of the cache. But what if there is no memory pressure? When there is no memory pressure, these execution plans are still going to stay inside the plan cache, such that there might be other user who might come tomorrow and use the same execution plan for his query. That's how the ghost cleanup works. Now, in the very next minute, the lazy writer will kick back in again to see if there are any least recently used execution plans. In our example, plan 2 will be used here. So what the lazy writer does is it will go ahead and increment the complexity countdown value for the plan 2 to its original value, which is 9. That's how the lazy writer and the goose cleaner process will manage the plan cache. Now let's go ahead and see how the buffer pool gets managed. As you know, the buffer pool will hold the 8 KB data pages and the index pages in it. Basically, the buffer pool has to manage 3 kinds of different structures: the heaps, clustered indexes, and the non-clustered indexes. Let's take an example of a heap table. Like you wanted to do a select star from a heap table. You know what will happen. The buffer pool has to go ahead and grab all those data pages into the buffer pool to do the select, right? But instead, which is very IO intensive, to do a select on the heap, to place all these data pages into the buffer pool, it's very IO intensive because the buffer pool has to go many trips to the disk subsystem to grab those pages. But instead, if you put the clustered index and non-clustered index on the top of the heap table, it will help reduce the IO because now the buffer pool has to go ahead and grab a few pages into the buffer pool, which will reduce the IO as well as speed up the query process. Now, how does the buffer pool gets managed? There is something known as checkpoint process, which will be kicked in every couple of minutes by the SQL Server automatically. Now, what it does is it will go ahead and check if there are any dirty pages inside the buffer pool. Now, what are these dirty pages? Dirty pages are the data pages which are already modified inside the buffer pool, but they are not yet hardened to the database file system. So once the checkpoint process kicks in, it will go ahead and grab all these dirty pages from the buffer pool and push them back to the database file system and harden them onto the disk. That's how the checkpoint process works. You can also manually run the checkpoint process by executing the word checkpoint in your management studio. Now, when you execute the word checkpoint, it will go ahead and grab these dirty pages and push them back to the database file system. That's how the checkpoint process will manage the buffer pool. Now, this is the very important slide, how SQL Optimizer will choose the plan. As you know, the SQL Server Optimizer is a cost-based optimizer. It always wanted to choose the good enough plan instead of the best plan. Now, what is the difference? The time and the cost is the difference. Let's take an example. Here, the left side, you see a select statement which have a 4-table join in it. On each table, we have a clustered index and 3 non-clustered index on top of each table. For example, if the optimizer wanted to choose the best plan instead of the good plan, what it have to do? First, the optimizer have to go ahead and analyze 72 different types of physical access methods per table. We have a 4-table join here. That means 72 times 4 physical access methods. Now, what are these physical access methods? Optimizer have to go ahead and choose whether it have to do the clustered index scan or seek, or whether it have to do any lookups, those kind of physical access methods, 72 per table. It have to analyze. On the top of it, it have to go ahead and analyze 24 different types of logical join orders just for this simple select statement. Now, what are these logical join orders? Here we have a 4-table join statement, right? For example, if the join between A to B is filtering out around 60% of the records from the result set, and the join between B to C is filtering out around 80% of the records from the result set. In that scenario, the optimizer will go ahead and reorder the join in such a way that it will push back the join between B to C front of the statement and the join between A to B back of it. Now, why the optimizer does this is because the join between B to C is filtering out more records, like 80% of the records from the result set. So it wanted to grab the results as quickly as possible That is the reason it will go ahead and reorder the join behind the scenes. On the top of it, optimizer have to go ahead and analyze so many transformation rules that out of all of those transformation rules, it will grab approximately 26,000 possible plans. Out of those plans, it have to decide the best plan. Now just imagine how much time and resources it have to consume to get the best plan for this simple select statement, which have a 4-table join in it. And no user wanted to wait for such long time to get the execution plan, right? To get the results. So that is the reason why the SQL optimizer, instead of going ahead and analyzing all of these transformation rules, it will just go ahead and analyze some of the transformation rules to get that good enough plan. I would like to thank Kevin Klein for loaning me this example. If I explain the same concept in a very simple words, let's take a query that we are sending to SQL Server, and the optimizer thought it is better to get the strategy like the plan A, execution plan A. It found the good enough execution plan A in 3 milliseconds and the execution plan B in 3.5 milliseconds. But in order for it to know if the plan A is better or B is better, it have to go ahead and analyze so many transformation rules for 5 minutes. Optimizer doesn't want to do that. It won't go to the third step at all. It will just go ahead and it will grab the plan A or plan B randomly. That is the reason why the SQL optimizer is so quick. Now let's talk about the life cycle of a query. If the life cycle of a query is divided into 3 different steps, then the first step contains the components parser, binder, simplification, and the trivial plan. All these components from the first step are very simple. They are very lightweight to the SQL Server. They doesn't require much metadata at all, except for the table definition, query definition, those kind of little things. It's very easy for the SQL Server to process these steps from the first step. When you come to the second step contains the components, load metadata, join heuristics, search phases. All these components from the second step, they require most of the metadata to process any query. When you come to the third step contains the components, access methods, transaction manager, and buffer manager. Now, when you compare the first step components, second step components to the third step components, the third step components are very IO intensive. Now, why I say that is because we have buffer manager here. It have to go ahead and interact with the disk subsystem, which is very IO intensive, right? That is the reason third step components are way too expensive. Now, the first step components and the second step components will come under the relational engine, and the third step components will come under the storage engine. Now, let's go ahead and see. First, let's talk about how the select statement runs behind the scenes, right? Here, a user wanted to run a select statement to the SQL Server, and he's waiting on the results, right? So no matter what kind of interface he is using, he might be using SQL Server, he might be using SQL Server Management Studio, Azure Data Studio, .NET Visual Studio, or even a third-party application. No matter what kind of interface he is using, he should first get the secure network connection to the SQL Server. Now, how does he get that? There is something known as SNI, which is also known as SQL Server Network Interface. Now, this SQL Server Network Interface, it will use the Internet Protocol to secure the network connection between the SQL Server as well as the client. The client is our user here. So no matter what kind of Internet Protocol the SNI uses, like it might be using TCP IP, named pipes or shared memory, no matter what kind of Internet Protocol we use, the process remains the same. So once the secure network connection has been established by SNI, the query that the user is sending is wrapped inside a tabular data stream packet, which is also known as TDS packet. And this particular TDS packet is given to the SQL operating system by SNI. Once the TDS packet has reached the SQL operating system, first the SQL operating system will identify that coming connection as a SQL connection, and it will assign a SPID to it. You know SPID, right? SQL process ID. When you do the SP-who2 or SP-who, you see those SPIDs, SPID number 65, 79. Those kind of SPIDs are the active connections made to the SQL Server. So once the SPID has been assigned, this particular tabular data stream packet here at the SQL operating system, it will be unwrapped, and that particular query is identified as a SQL query, and that query will be now sent to the first step of the relational engine. So the first step of this is the first step of the relational engine. We have 4 components in it, right? The first component is the parser. Parser, it will just parse the query. That means it will go ahead and check if there are any syntactical errors inside our query. Like, let's say an example. I wanted to do a select star from a table, but by mistake, I given select star form. At that particular stage, the parser should identify that it's a syntactical error and throw back me an error saying it is syntactically incorrect. And variables are declared here. Whether you are declaring the variables properly or not, those kind of things are checked here. Views are also expanded. Like if you are running a query and you have views inside your query, the query text behind that view is brought inline into the code you are sending. Now with all this information that it has gathered, the parser, what it does is it will put a hash on the query that we are sending. And it will go ahead and check against the hash of the execution plan inside the plan cache. It will go ahead and check if it can find the exact match of the execution plan. If it finds the exact match, then it will go ahead and use the same execution plan for the execution phase. But what if it didn't find the execution plan, right? It will go ahead and build the initial logical tree for the first time. Once the initial logical tree has been built, the query will be now sent to the binder component. At the binder component, binder will go ahead and check and validate the objects, like whether the columns objects that we are using in our query, they are valid or not. Parser is the one which will just validate the syntax, but the binder is the one which will validate the objects, like columns, tables, whether they are valid or not. Binder is also known as algebraizer or normalizer. Binder will also go ahead and check user permissions, whether the user that is running the query, whether he have enough permissions onto those objects or not. Those kind of things are checked at the binder component. Data type resolution also happens here. Now, what do I mean by that, right? The data type resolution. Let's take an example of a simple select statement between the 2 tables, and we are using union all clause between both tables, right? The ordinal column of those 2 tables should match in their data type. We are going to see inside our demo a particular example based upon these data type resolution. Aggregate binding also happens here. Whether the sum, average, those kind of things are bound here. Now with all this information, the binder component will go ahead and update the parse tree inside the plan cache. And then our query will be sent to the simplification component. As the name itself says, simplification will go ahead and simplify the query. Now, how does it do that? For example, if you are using subqueries in your query, right? Behind the scenes, simplification will just go ahead and convert those subqueries into simple joins. Inner join, outer join, those kind of simple joins. So no matter how many times you are sending those subqueries, simplification component will convert those into simple joins behind the scenes. Contradiction detection happens here, like whether if you have like foreign key contradiction. Let's take this as an example, like foreign key contradiction. Those kind of contradictions are detected here. Now with this information, the parse tree is once again updated. And now our query will be going to the trivial plan component. Let's take an example. Let's say we are running a very simple query to the SQL Server, like select star from a table or select star from a table with a simple where clause. Those kind of queries are treated very simple by the SQL Server. Now SQL Server will think this way, this is such an easy query. Why should I even go ahead and update the parse tree inside the plan cache that this previous component has been built? Why should I even consider that? I will just go ahead and discard that parse tree inside the plan cache, and I will go ahead and create the trivial plan on the fly because it doesn't cost it much. It doesn't cost any resources to create those trivial plans. And by default, these trivial plans are not saved inside the plan cache because SQL Server think, why should I even go ahead and save these trivial plans? These are so simple to create. I do not want to waste the memory inside the plan cache for these simple query plans. Let me go ahead and save the same memory for the more complicated execution plans, like the full plans. So once the trivial plan has been generated for this very simple query, that trivial plan will go for the execution phase. But what if our query is not simple? What if our query have 10 tables in it with a very complicated logic in it? SQL Server will think, let me go ahead and create a full plan for this query. So once that complicated query will reach at the trivial plan, it will go ahead and send that query to the second step inside the relational engine. So the first component inside the second step of relational engine is load metadata. At the load metadata component, most of the metadata that it have to gather to process any query are be processed here, right? Like let's say the index statistics kind of things are gathered here. Now, what are these index statistics? Statistics are the blob structures which are saved inside the system tables to describe the distribution of the data inside a column or set of columns or an indexed view. So basically, the query optimizer will go and trust and use these statistics to analyze how many rows does it think might come out of a table, right? Those kind of statistics information are gathered here. Auto create statistics also happens here. Let's say you are running a select statement and searching on a column very frequently, and that column is not in the key columns of an index. SQL Server, in that case, it will go ahead and auto create stats on that particular column because now it wanted to go ahead and use that information inside the stats to get to know how many rows does it think going to come back out of that particular column. It can use that for generating the execution plans. Those kind of information are gathered here. SQL Server and Windows collation are checked here. The cardinality estimates that we were discussing, right? The statistics information are gathered here. Set options are also checked here. Like let's say set XML on or off. If you are using like ANSI padding on or off, depending upon on or off setting, the execution plan might be dependent. Now with all this information, the parse tree inside the plan cache is once again updated, and our query will be now sent to the join heuristic component. At the join heuristic component, reordering of join happens. Like in the previous slides, I have explained what is this reordering of join, but let me explain again with a very simple example. Let's take a very simple select statement between the three tables, and we have join in between those three tables. Let's say the join between A to B is filtering out around 60% of the records from the result set, and the join between B to C is filtering out around 99% of the records from the result set. In that case, the optimizer will go ahead and reorder the join between B to C front of the statement and push back the join between A to B back of it. Now, why the optimizer does is because it wanted to grab the results as quickly as possible. With this information, the parse tree inside the plan cache is once again updated, and our query will go to the search phases. In the very next slide, I'm going to discuss what these search phases are. But for now, just remember that the optimizer is a cost-based optimizer. It always wanted to choose that good enough plan. Now, optimizer will go ahead and grab that information, that execution plan information from these three phases, the phase 0, phase 1, and phase 2. Once it gets that good enough plan, it will go ahead and update that information inside the plan cache. And then finally, a hash is put on that particular query tree inside the plan cache. And then our query will be now sent to the storage engine component, which is the third step. But before going into the third step of storage engine, let's go ahead and see what these search phases are. Now, no matter what kind of query we are sending to the SQL Server, optimizer have to go ahead and grab the information, the execution plan information from these three phases. The phase 0 is known as transactional plan. Now, most of the execution plans are generated here at the pre-optimization stage. Now, what is this pre-optimization stage? The first step inside the relational engine, which are those four components, right? The parser, binder, simplification, and the trivial plan. Those components come under the pre-optimization stage. Now that means the trivial plans are generated here, right? So these trivial plans are generated. Execution plans at the phase 0 are created as quickly as possible, and for the queries with maximum of 3 tables in it. Very basic heuristics are needed here to create these execution plans, like table definition, query definition, those kind of basic information. Now, when you come to the phase 1 is also known as quick plan. These execution plans are created for the queries with maximum of 8 tables in it. Most of the transformation rules are needed than the phase 0. Now, what the optimizer does is, in the case of phase 0 and phase 1 is, optimizer will go ahead and compare the query with already existing execution shapes. If it finds that good enough plan, it will go ahead and grab that information from these two phases. But what about the phase 2? Phase 2 is completely different. Phase 2 is known as full plan. Full plans are generated here at the phase 2, and these queries are more complicated queries, right? These execution plans are created for more complicated queries, and most of the parallelism spills and spools to the tempdb happen here. And most of the transformation rules are unlocked here. Now, optimizer, not like the phase 0 and phase 1, what the optimizer does for the phase 2 is, it will go ahead and first prune off all the transformation rules it is not using. Now, what do we mean by that, right? Let's take an example. Like you are running a select query to the SQL Server, and in that select query, you do not have a varchar max data type. Let's take this example. First, the optimizer, it will go ahead and prune off all the transformation rules which are related to this varchar max data type, so that it can go ahead and analyze some of the transformation rules as quickly as possible to get that good enough plan. That's how the optimizer have to go ahead and grab that information from these three phases. Now, our read transaction, right? We plan to do the read transaction first. So our read transaction is at the third step of storage engine. No matter what kind of query we are sending to SQL Server, read or write, it have to pass through the first step of relational engine and second step, and then come to the third step of storage engine, like based upon how complicated your query is. If your query is so simple that SQL Server thought it would be really easy for it to create the trivial plan, it will go ahead and create the trivial plan, and it will come to this third step of storage engine. But if the query is complicated, then it have to pass through the second step and then come to the third step of the storage engine. But all the difference happens here at this storage engine phase for the read as well as the write transaction, right? Let's go ahead and see what those differences are. And first, let's talk about how the read transaction happens. So the first component inside the storage engine is access methods. Access methods, this particular component by itself, it doesn't perform any action, but it have to analyze how it have to grab that results from the database file system. That's all it do. Now, when the query goes to the transaction manager component have two subcomponents in it, the log manager as well as a log manager. Now, as this is a read transaction and we are not modifying any data pages inside the buffer pool, we do not have to invoke the log manager part of it. That is the reason the transaction manager will just go ahead and invoke log manager part of it, and it will go ahead and request the buffer manager to put a shared log on the resources it needs to process the query. Now, why shared log? Is because we are not modifying any data. We do not want it to block other users. That is the reason the shared log. So once the query has reached to the buffer manager, first the buffer manager will go ahead and put shared log on the resources it needs. Then it will go ahead and check if all the resources that it needs are already inside the buffer pool. If it didn't find some of them or all of them, it will just go ahead and grab those pages in the form of 8 KB pages, put them back inside the buffer pool, do the operation there, and send the results to the user. That's how the read transaction works behind the scenes. Very simple. Let's go ahead and see what happens for the write transaction. Now, all the difference happens at the transaction manager component and buffer manager component for read and write transactions. Now, let's see what will happen at the write transactions. Access methods by itself, it doesn't perform any action, but it have to analyze how it have to grab the results from the disk subsystem. Once the query has now reached to the transaction manager, now before writing anything inside our data pages inside the buffer pool, right? Before modifying anything, we have to first write those changes into the transaction log. So the transaction manager for the write transaction, it will first go ahead and invoke the transaction log, and it will have to first write all those modifications before modifying any data pages inside the buffer pool. It have to go ahead and write those changes, and then the transaction manager will go ahead and invoke the log manager part of it. Now it will go ahead and request the buffer manager to put an exclusive log on the resources the buffer manager needs to process the query. Now, why the exclusive log is because it's a write transaction, and we do not want other transactions to be interfering with our transaction, which is again the ACID properties which we have discussed earlier in this session. Once the query has now reached to the buffer manager component, buffer manager will first go ahead and put the exclusive log on the resources it needs, and then go ahead and check if all those resources are already inside the buffer pool. Then if it didn't find any of them, it will go ahead and grab those pages in the form of 8 KB pages, just like the read transaction, put them in the buffer pool, do the modification, and then send the success message to the user. Now, did you observe something here? The data pages have already been modified inside the buffer pool, but they are not yet hardened to the database file system, right? That's when the checkpoint process, it will be kicked in every couple of minutes by the SQL Server automatically. It will go ahead and grab these dirty pages out of the buffer pool and put them and harden them onto the database file system. That's how the write transaction works. Now let's go ahead and see a very quick demo. I will show you how the pre-optimization stages works behind the scenes. We can see that inside our management studio. Now, pre-optimization stages, meaning parser, binder, simplification, and the trivial plan components. How do those component works? Let's go ahead and see. Kevin, are you able to see my management studio? Can you confirm?
Yep, it's looking good. If you could bump up the font just a tiny bit, that'd be great.
Oh, okay. How about this?
Hit Control minus to go one step down. That's huge. It's great.
Okay. How about that?
Yeah.
Let me go ahead. Maybe 125 should work.
Yeah. There you go. Perfect. Thank you.
Thank you. So in my demo, I'm going to show you how the pre-optimization stages works, right? So we are going to use the AdventureWorks 2016 database here. Let me put the database in the context. And then let me first show you how the parser works. So I can enable the parser in two ways. I can set the parse only option to be turned on, or even I can do this button over here, right? The parse button inside the management studio. But let me set the parse only option on by using the query. So when I enable this parse only option on, it doesn't execute the results or it doesn't generate any execution plan. All it does is it will go ahead and check if there are any syntactical errors. Let me go ahead and run this very simple select statement. We do not have any syntactical errors, so it should run fine. Now, in this particular select statement, variables are also declared at the parser component, right? I did not declare a variable here, but still I am going to use in the where clause. So when I execute that, it should say must declare the scalar variable. It is a syntactical error kind of thing, right? Variables are also declared here. And they are checked here at the parser component. So let me go ahead and do select non-existing column from a non-existing table. Let's go ahead and see if this will go through. Command complete successfully. Now why is that? Is because syntactically it is fine, right? It is right, but the objects are not valid here. That's when the binder component should kick in, right? The binder component is the one which will validate the objects. Parser, it doesn't validate the objects. So let me go ahead and set the parse only option off. Let me go ahead and set format only option on this time. When I set format only option on, it will go ahead and invoke both the parser as well as the binder components together. It doesn't execute the results or it doesn't generate any execution plan. Here, this is a very simple select statement. All the objects are validated. So all the objects are valid and then syntactically it is correct. So it should run fine. But here, let me go ahead and do the same select statement which selects non-existing column from a non-existing table. But this time, the binder component will be kicked in together, right, with the parser. So it says invalid object name. Let me go ahead and set format only option off. And let me show you how the data type resolution happens. This is a select statement between two tables. And the ordinal column of those two tables should match in their data type, right? The customer ID is of an integer data type here. And sales order ID is also of an integer data type. So when I execute that, it should run fine. It will produce the result because these both are the ordinal columns are of the same data type. But what if I go ahead and manually created a data type resolution error, right? The customer ID here is of an integer data type and credit card approval code column is of a varchar data type. Now, when I go ahead and execute that, it should throw me a conversion failed error, right? Because those both columns doesn't match in their data type. That's how the parser as well as the binder component works. Now let's go ahead and see how the simplification and trivial plan component works. Let's use the AdventureWorks 2016 database again. The simplification component will simplify the query, right, by converting those subqueries into simple joins. Now let me go ahead and run this select statement, which have a subquery in it. Let me go ahead and enable the actual execution plan on, and let's execute that. And let me go ahead and check the execution plan. Did you observe here? It actually converted that into the inner join, right? Behind the scenes, no matter how many times you send that subqueries, behind the scenes, they are converted into joins. And redundant joins are also removed at the simplification component. Redundant joins meaning here we are only grabbing the results like the column values from the sales order header table, but we are simply using the customer table. We are not getting any values from that table, right? So when I go ahead and execute that query by enabling the actual execution plan on, when I execute that, when you check here, it just went ahead and grabbed the results from the sales order header table. It did not touch the customer table at all. Now, why is that? Is because these both tables do have the relationship between them, like the foreign key relationship between them. So SQL Server, when we executed this particular query, SQL Server thought it is of no use to go ahead and touch the customer table because we are not getting any values from them. And also it trusted that relation. But what if we do not have the relationship between those two tables, right? In that scenario, definitely SQL Server have to go ahead and check those values, right? It will go ahead and use the customer table also inside the execution plan. But since we have the relationship between those two tables, it just went ahead and ignored the customer table. And the contradiction detection also happens here, right? Here, this is a very simple select statement. We have where territory ID is equal to 1 and territory ID is not equal to 1. So when I execute that particular query, it should not give me any results. Now let's go ahead and see how the trivial plans are generated. This is a very simple select statement with a simple where clause. We are using AdventureWorks 2016 database. Now let's go ahead and see if SQL Server thinks this is a very simple query. My actual execution plan is turned on. Now when I go ahead and do the properties on this particular select and see the optimization level, it has actually went ahead and created the trivial plan, right? SQL Server thought this particular query is so simple and it do not wanted to generate the full plan. Instead, it will go ahead and create the trivial plan because it doesn't cost any much resources to create this trivial plan. And this particular trivial plan is not saved inside the plan cache. Trivial plans are not saved by default inside the plan cache. But let's take an example, like you are expecting a query to create a full plan, but SQL Server is going ahead and creating a trivial plan for it. And you want to save that plan inside your plan cache, but there is no way to save that plan, right? These trivial plans are not saved inside your plan cache. Instead, if you can convert that trivial plan into the full plan, that plan will be now saved inside the plan cache. So here, you can convert the same select statement in that it got created the full trivial plan. You can convert that into a full plan by enabling the trace flag 8757. If you use that trace flag inside your query, it is only bound to that query. It doesn't affect the server level or the database level. Now let me go ahead and run that particular select statement by turning on this trace flag, right? When I execute that and go to the execution plan, to the properties on this particular select, it has just converted the same trivial plan into a full plan. And now this particular plan will be saved inside the plan cache. I do not suggest you to do this in production because there is a reason why SQL Server thought to create the trivial plan, right? It doesn't cost it much. So no matter how many times the user run these kind of simple queries, SQL Server will just go ahead and create the trivial plan. But there is this option, you can turn them into a full plan. Now that is the demo for this particular session. So in Start Thinking Like the SQL Engine session, we have started with the basics, the asset properties. We have gone through the overview of what are these asset properties and why it is so important for all these relational engines should satisfy the asset properties of transaction. And we have also seen an example ensuring the asset property. We have gone through the overview of different types of components we have inside the memory architecture of SQL Server. In this particular session, we mainly focused on how plan cache and the buffer pool get managed. And we have also seen the life cycle of a query for the read as well as the write transaction, like what happens behind the scenes at each component inside the SQL engine. And we have also gone through the overview of like all the components, right? We have gone through the different types of component inside the SQL engine. That's relational engine components as well as the storage engine components. In order for me to prepare for this presentation, I have followed many resources, but these are the main ones. If you wanted to know more about the SQL Server internals and architecture, please follow these resources. I would like to thank Kevin for giving me this wonderful opportunity one more time. Thank you so much. And if you have any questions, this is the right time.
Yeah, thank you. Thank you. So we do have a couple of questions that came in fairly early on. For anybody who has questions now, this is a great time to start typing them in as we answer the first couple of questions so that we get a nice stream of questions flowing through. The first question I want to ask is, for the SQL Server memory architecture diagram, is there an OS isolation layer for OS related dependencies?
Yeah, resource governor, right? But I did not mention that.
Okay.
I just mentioned the inside of SQL Server, but the
Gotcha.
resource governor will be managing these, right?
That's fair. Yeah, that's true. All right. The next question, is there a way to force SQL Server to get the best plan?
That's very interesting question. For example, let's take if your query is so complicated, right? If it goes and wanted to create that full plan, that third step, like we have 3 phases, right? Phase 0, phase 1, and phase 2. At the phase 2, it will try to get that good enough plan, but if it didn't find the good enough plan out of that phase 2, then it has to actually throw back the error to the user. I think if you wanted to generate that best plan, optimizer is not designed in that way. I'm like, we can't force that, right? Inside the optimizer, I think there is no option that we can force that. Kevin, do you know the answer for this? Because I think it can't, right? It will just go ahead and get that good enough plan as quickly as possible.
Yeah, that's about all that we can do. There are some tricks that I know you can do around turning on and turning off specific checks. But there you're getting into some shenanigans. There's no easy way to say, yeah, just go and give me the best plan you can possibly get, or even to say, I'm willing to give you half a minute to find the best plan because this query runs in 4 hours, so an extra 30 seconds, if it saves me several minutes or even half an hour or so, I'd happily let it run for that extra half minute. But we don't really have any control over that.
Right.
I got a couple of people said, very clearly presented, very interesting and informative. Thank you. Both said thank you.
Thank you so much.
So anybody else with questions or thoughts for Deepthi?
Or any feedback will be appreciated.
Mark says, outstanding. Tommy says, very good presentation. I do hope you can come back and share more of your knowledge.
Thank you so much.
Absolutely. Yeah, I agree. I agree. We'll get Tracy to figure out a place on the schedule. It may not, we'll see. The schedule's pretty full for this year, but we'll try to work something out. The Mark who asked the question about the optimizer responds with a sad face. I agree, Mark.
Oh man, we know that we want the best plans, but then
yeah. Though if you think about the logistics of it, where you start talking about the type of query where I'd really care, you start like 10 to the how many power options are available?
At least some thousands. I do not know the exact value, but you mean the transformation rules, right? That is what
Yes.
you're asking?
Yeah, like when you
at
start
least
talking,
some thousands of them.
Right. So it's thousands of transformation rules, and when you think about all the permutations of ways in which you can apply those rules individually, like even when you start talking about like 10 to 15 tables,
Right.
the number just gets huge.
And the other point I have to mention is sometimes I told you, right, those three phases that the optimizer have to go ahead and grab the good enough plan information. Sometimes what happens is if it have to go to the phase 2 to get that full plan, and in some scenarios, even after doing so much of like analyzing transformation rules, it cannot get that plan. And for that particular query, based upon how they wrote the query and how complicated, if it is too much complicated, it will just go ahead and throw an error. It can't generate a plan. In some scenarios, that might happen.
I've seen that error.
Really? I did not.
It's nasty dynamic SQL, and like when you start talking about an in clause with so many different options, and I don't remember many of the specifics, but every once in a while the error would pop up and it's like, oh yeah, you're trying to do too much. Do a little bit less and this will work.
And if you want to contact me, it would be awesome. Like I would like to contact with you guys. So here is my Twitter account at DBA Nuggets. Yeah, if I can get the other chance, like I have a wonderful session on statistics, especially. Like as Kevin said, there is no like all this year got booked. But if any other speaker get like, if there is like, if they have to skip it for that month, you can just contact me. I'm available and I would love to speak to your user group one more time.
Definitely. I'll set you up with Tracy and we'll keep you in mind if there is anything that comes up. So Tommy asks, can we get a copy of your demo scripts?
Oh, definitely. So is there a chat window over here? Can I share or?
Yeah, and then I'll share it with.
Oh, just a minute. It's on my GitHub. I'll give you in a minute. So the session title has changed, but then all the contents are the same. Let me go ahead and share the chat window.
Don't worry, chat. You're still the best chat. This is only the second best chat.
Did you get it, Kevin?
Yep, got it. Thank you.
Awesome.
So that's the link to where you can grab the demo scripts and everything, Tommy. Mark follows up and asks, are there third-party products that might help, I guess, with plan optimization?
I don't think so. Kevin, do you have any information on that?
Closest I've got is basically if you're looking at your query tuning, something like Century 1 Plan Explorer, but still that's going to be helping you write a different SQL query that will perform better versus telling the optimizer to behave differently. That's essentially the optimizer is supposed to be a black box.
Right. We cannot actually modify, but then you can see those query plans and then tweak into your code, and and try to impress our optimizer to generate a good enough plan for us.
Yeah, exactly. So it's not exactly a full black box. Like there are ways that you can use trace flags and
then
different
statistics, right? Statistics. If you are up to date with your statistics, then that will affect how much memory grants are allocated to your queries, and that will also improve your performance. You have to make sure you have good indexes, not like too many, and then your statistics, make sure they are up to date, right? That all will help to the better performance of your queries.
Yeah. Yeah. So Mark, at that point, we're talking more about query tuning versus optimizer internals.
That will be a wonderful topic, especially the optimizer. Wow.
We actually did have Kevin Klein for the first advanced DBA meeting that TriPass ever did. Kevin came in person and did a 500 level session on the ways that the optimizer can that you can tweak the optimizer. We're talking about some detailed level stuff that I would not personally be comfortable with doing in a real environment.
Right.
But it was kind of cool to look behind the scenes a bit at how that process works.
Absolutely.
Okay, anybody have any other questions? Now is a great time to get them in. Actually, 10 seconds ago was the perfect time to get them in. This is a good time to get them in. 15 seconds from now is not a great time, because if you're not in there by 15 seconds, we may not be able to get to it tonight. So get your questions in, please. And while you're doing that, quick reminder, or for people who jumped in the middle of the stream, that the Triangle Area SQL Server Users Group is looking for a new board member. If you are a TriPass member in good standing, chat, contact me, get a hold of me somehow, and we can talk about what that board member position looks like, what the responsibilities are, and how everything works. And we'll announce a new board member at some point in the future once Tom Norman has officially resigned his position and we have a replacement ready to roll. But if you want it to be that replacement, get in touch with me, please. And with that, looks like no more questions. Mark is happy. We've made him happy. So
thank you, Marcus.
So thank you again so much for presenting tonight. We appreciate you taking the time to do so.
Thank you so much, everyone, for joining the session today. Thank you, Kevin.
Absolutely. And we'll catch you folks next time. Next week, we have another meetup scheduled. So check that out, meetup.com/TriPass, and see you next time. So until then, everybody, take care.
Take care. Good night. Bye.